Hello and welcome to this video on hash puzzles. In general, the Bitcoin consensus mechanism is the protocol where essentially the parties in the network agree on the next block. And one part of this protocol are essentially hash puzzles. So in this short video, we will take a closer look at them. We will understand what they are and also understand the properties that the hash function needs to fulfill. So usually when you think about puzzles, you might be thinking about something else. In fact, you might be thinking about the typical thing that we are playing as a kid. So either it's this typical puzzle where we try to fit in the pieces together, or there's this magic cube where you have to find a solution in order to complete it. So what does this have to do with actual cryptographic hash puzzles? Well, in some sense, the idea is very similar. In a cryptographic hash puzzle, the computer has to find a solution. And essentially the idea to find the solution is that you have to search in a very, very large space. And finding the solution in that space, there are no shortcuts. You essentially have to do this, we call it brute force, which means you have to try out all possible solutions. As we sometimes did with the puzzles, right? We tried to fit them all and it didn't work. So let's just try one after the other. So the first property that we need to define a hash puzzle is something that is known as hiding. So intuitively, when I give you the output of the hash function, many people believe that this output actually completely hides the input. Well, in many cases, this is actually not true. In general, we have to think about the underlying cryptographic primitives and assumptions that we use. Similar is this here for the case of hiding. In particular, if you assume that your hash function is collision resistant, then in fact part of the messages might be leaked. There's nothing wrong with this and it doesn't contradict the corresponding notion of security. Even worse, if your hash function is not compressing, then it might be the case that it's just the identity function and your full pre-image will be revealed. Therefore, we need to define hiding as an additional property. And this property essentially says, as you can see here, that if I give you the output of the hash function, then essentially with high probability you cannot recompute or predict the pre-image. Note that this definition also strongly depends on your input. Think, for example, about hashing passwords. Passwords usually come from a small space. Formally speaking, they have low entropy. So if I give you the output of or the hash value of a hashed password, then in general you can simply brute force the password by trying them out all. Which means your notion of security also strongly depends on the input distribution. And therefore, in order to come up with a meaningful notion of security, we also need to make sure that one additional input to the hash function has high entropy. So at this point you might think about it as just being a uniformly random string. And if this string is large enough, then no matter from which distribution the other element was chosen, it is very unlikely, if the hash function has this property, to recompute the pre-image. Now, if we have a hash function that satisfies both properties, first of all being collision resistant, and second being hiding, then we can obtain a very fascinating cryptographic primitive, and this is the one of a commitment. What is a commitment? Well, a commitment is a cryptographic property or primitive between two parties, say Alice and Bob as always. So let's assume that Alice wishes to commit to some value. And what she will do, as you can see here, she will essentially put the value inside of her safe. And then she will essentially send the safe over a channel or give it to Bob. And now, because the safe is closed, right, Bob can just not figure out what is inside. On the other hand, there's a second property, and the second property essentially says that Alice cannot change her mind afterwards, right? So she cannot go to Bob and say, oh, sorry, I forgot something, I just need to enter there a different message. This doesn't work because Bob would notice it. So commitments have many applications in cryptography. In general, we use them for zero-knowledge proofs and for many other things as well. And the construction that you can see here is actually super simple. Well, let's take a look at it. Intuitively, we will consider two different stages. The first one is the commit stage, and this is the point when Alice needs to fix her opinion or essentially need to fix her message. So how is this done? In order to commit to this message, what Alice will do, she will compute the hash value using this random string together with the actual message that she wants to commit on. And then she essentially gives this hash value over to Bob. This concludes the committing stage. And then in the second phase, we have the opening phase. And in the opening phase, Alice will reveal both the message and the randomness, and will give it to Bob. Now Bob can recompute the hash value and check if the message indeed was committed or not. So at least on an intuitive level, let's try to think about the security properties. Well, we have just learned that the notion of hiding says if we choose a string that is long enough and random, and then we obtain a property that we call hiding. So if the hash function is hiding, then it means that it fully hides the message that Alice wanted to commit to. In other words, when Bob received this commitment, he doesn't learn any information about the hidden message. On the other hand, what about the binding property? Remember that the binding property was the point that Alice cannot change her mind afterwards. Well, she already gave the values m and r after computing the hash values to Bob. And now it's on her to reveal the corresponding preimages. So if she tries to find a different message m prime, then it essentially means that we have two different values, m and r, from the commitment, and the second pair, m prime and r prime, and they both must match to the same output of the hash function. Otherwise, Bob will not accept this as a valid opening. Now, if she's able to do this, it essentially means that she can break the collision resistance directly of the hash function. So here you have seen a very nice application of hiding and collision resistant hash functions. It's very efficient and very fast. So now that we have defined the notion of hiding and we actually saw great application of this, we're now going to introduce the notion that is called puzzle-friendly. Well, the hash function intuitively is puzzle-friendly if there are no shortcuts, which means in order to find a valid solution, then the best thing that the computer can do is basically just trying all values out. As an example, let us consider this image here. What you can see on the left side are the possible input values, and what you can see on the right side are the evaluations of the hash function. Well, first of all, you might notice that in this definition there, or in this picture, we just found a collision, but this is just some joke that I made here. More important is this big bubble that you can see there. So the idea is essentially that you have to find a value such that the output of the hash function actually maps to this target. Right? So there might be many possible solutions that go into this space, but at least this space you have to hit. And then you found a solution for the corresponding puzzle. And the last thing that we need to define for such a search puzzle is actually a way to adjust the difficulty and also to express what is the solution. Well, intuitively, if we've just seen, a solution is essentially a value where the evaluation of the hash puzzle goes into this big bubble. But now the important thing is, and this is actually necessary for Bitcoin, is to make sure you can choose the size of this bubble depending on the actual hash power. In other words, if there are just only a few people finding the solution or trying to find the solution, then you can make this puzzle easier. But if there are many people doing that, or in other words, if there's a large fraction of hash power, then you will make this bubble smaller. The reason why we actually do this later in Bitcoin is that we want to make sure that there's always a fixed time in which we actually find a new block. Right? So finding a new block will correspond to finding a solution to this hash puzzle. I know that might be now already a bit far, but we will come back to this in our lecture about Bitcoin and its ingredients. So this brings us already to the end of this video. In this video we discussed the notion of hash puzzles and we'll actually discuss what kind of properties a hash function needs to fulfill in order to serve as a cryptographic basic for such a puzzle. So I hope you liked the video, and would be glad if you press thumbs ups or leave a comment, and I hope to see you in the lecture soon, or maybe just here and online. Thank you.